All right. Hello, everybody. It's yours truly, Mr. Ogle, here to teach you about the law of universal gravitation. So we are going to be taking notes today, so go ahead and grab your notebooks, open them up to that first page, and we are going to start a new section. So I know that you did your notes virtually, right? So we had you put the notes together in in a Google Doc to start this one out. So if you want to leave a couple pages blank, make a title page, gravity, you can do that, and or just start out with these notes right here. 12.8, the law of universal gravitation. I was just looking right now. It's not 12.8. It'll be 12.10. So 12.10, law of universal gravitation. Down here you have a couple links, which is one to the gravity, CK12, and the other one is your acceleration due to gravity, and that's something that you'll be having for an assignment today after the notes, which you should probably get that done in class, be free for the weekend. Nobody wants homework on the weekend. All right. All right, so again, push pause if you need to, and we will move right along. Now, you may have heard a story about an apple falling from the tree and hitting Isaac Newton in the head, but I am here to tell you, dun dun dun, now that story is not true. But seeing how things like apples have fallen to Earth helped Newton form his ideas about gravity. And this idea that the force of attraction between things that have mass. Right, and so we're looking at that apple, it has mass. The earth, it has mass, right? Sir Isaac Newton, right there, has mass, right? And so we would say that that apple, once it's, came towards Earth or is just sitting in the tree, is actually exerting a force towards Earth, right? And when it actually hits Earth, right, there's a force there as well, right? All right, so we see this picture of the Earth, and the idea here is that we're kind of familiar with gravity, right? We've heard that word before. We know a little bit about it, and the idea that Earth's gravity that we already are kind of familiar with the idea that Earth's gravity has a force that is constantly pulling matter, us, right, anything else around us, towards the center of the planet, right? So it's pulling us down. Right, and that's why on this round Earth, right, we fly across to the other side of the planet. We're not standing on our heads, right? So whichever way we are situated on the Earth, we're being pulled towards the center. As the contact force, gravity gives us weight, right? That's we hop on that scale and like, oh my God, right, too much, right, or maybe not enough, and it prevents you and everything else on Earth from being flung out into space as the planet spins on its axis, right? And now we have seen movies where different people are on different planets and or in outer space itself, and they just float away, or they're just floating, right? There's no gravity. There's nothing pulling them to to Earth, right, or to the planet itself. And different planets have different gravitational holds, right? And that's something that also excited people about Mars, right? So we're always talking about Mars and how it could be a possible other planet for human life if our Earth does not sustain itself. But that's a long way off. And the idea is that it does have a gravitational pull, right? And it does pull things towards its center. And then so this kind of pictorial, right? You see that airplane flying in the ground is pulled to the center of the Earth, right? You hold up a ball, drop it to your feet. Its ball is being pulled towards the center of the Earth. And then as we go around, and we see as the people are standing, what continent is that? That's South America, or no, that's South America. That is Africa. And you can see, that the ball would be pulled down towards the center of Earth. It wouldn't float off. And I guess I should maybe put the pointer on there for you so you see what I'm talking about. It's this guy right here, right? So he doesn't fall directly downward, right? It falls towards the center of the Earth. Right? So it's a cool little pictorial there for you to check out. Now, Newton's law of universal gravitation, that's what we're going to be focusing on here. And the idea of Newton's law, and this is going to be something that you're going to want to write down because it will be something that you might possibly be tested upon. So we'll give you some time. Mr. Halpern can also push pause for the video and then just let you write that down and then get on your way in a moment. But Sir Isaac Newton was the first one to suggest that gravity affects all objects in the universe. Okay, all objects. The force that causes an apple to fall from a tree to the ground is the same force that causes the moon to keep moving around the earth, right? And we see the earth, and something that you might notice or you may not notice, right? In the idea that how the earth is on a tilted axis, right? Something you probably learned a long time ago. And it is spinning, but the moon is also spinning around it in kind of a circular manner, right? So it's the earth is spinning on an axis, right? And it's moving around, right? That's how we have night and day, right? And then we also have the moon that is spinning at a constant, rate around the earth as well. And if everything didn't have that huge gravitational pull, right? If Earth wasn't this large, then we wouldn't have a moon, right? It wouldn't have a pull. It wouldn't hold that moon in place, okay? And so I'm sure you probably discovered that when you did your first initial research questions on that very first day. I think that was Monday or Tuesday for you guys. All right, so Newton's law of universal gravitation states the force of gravity affects everything with mass in the universe. So anything that has mass, no matter how small, exerts gravity on other matter. And we have this pictorial here, and we see that there's m, this is mass, the F is force, and then this is another mass. Okay, and something else to think about is that this mass and this mass are not even touching each other, but they are still there's still a gravitational force acting between them. Okay, so that's something that's hard for us to kind of think about because they're not touching, right? If we get on a dog pile, right, and people jump on top of us, you're feeling that gravitational force get heavier and heavier, and you're like, I can't breathe, get off, right? I don't know. That's my cousins used to do that to me all the time when I was growing up. And then, the bigger that we got, the heavier they got, and then I just stayed small, so I just got smushed. But anyways, another story, another time. And thinking about that, right? That mass is touching you. You feel that gravitational force. But think about, we're being pulled to the earth. Do we feel being pulled? No, right? We don't feel that pull, but we are. There's a force exerting on us. And so, although they're not touching, right? These two aren't touching, right? These two masses, no matter what they are still exerting a force, okay? So, I have a little key on the next slide for you that talks about what F, D, and M are, but these are the main variables in gravity, and that's something that you went through your PhET lab yesterday or the day prior, and talked about these two items. And so we're looking at this thing that factors that influence the strength of the gravity, right? And so in that PhET lab that we looked at when we change the mass, well, what happens, right? Well, when we double the mass, right, 1m, and we go to 2m, right, well, what happens to the force, right? And this is distance staying the same, right? So we see distance the same. This distance is the same as this distance, the same as this distance, right? And so we're looking right here and we're saying like, well, if double the mass, double the force. That's pretty easy, right? Triple the mass, triple the force, right? What happened here though? When we double the mass on both sides, well, we have 4 times the force. Right? And the m is mass, the f is force, d is distance, right? So when we keep distance the same, and whatever we do to the mass also happens to the force, right? So if we quadruple the mass, no matter if it's on the left and right side together, or if we go from 1m to 3m, we're still tripling the force, All right. Um, Now we're looking right here and we're saying that the change in distance, right? If we change the distance, we see that the distance, right, from the two objects, right, that are the same mass, if they're the same mass, and we double the distance, well, what are we doing to the force, right? It's 1/4 times force, right? And so when we think about that, when the mass stays the same, when we double the distance, the force is cut down by a certain percentage, right? I'm going to let you think about that for a second. And thinking about if I times 0.25 times something, right? What do I get? So if I take 5 and I times it by 0.25, what do I get? I get 1.25. What is that in relation to 5, right? What is that 1.25 in relation to 5, right? So it's a quarter of it, right? And so right here, if we take the distance, we can cut the distance in half from what it normally was. Okay, cut it in half. So it used to be this distance right here, right? Cut it in half, right? What happens to the force between them? Well, the force doubles, right? So if we make the distance greater, we see that the force exerted on the two objects is less. If we make the distance less, right? Cut the distance in half, we get more force. So we could say that the closer two objects are to each other, right, the more force that they're exerting on each other. Okay, the farther the two objects are, right, from each other, the less force that they're exerting on each other. Okay, so a good rule of thumb, just think about that. Again, what's going on with the little pointer? Pointer was freaking out there for a second. Now looking at this one, when we have double the distance, right? But we also double the mass, the force stays the same. Interessante, right? Very interesting. So when we double the distance from the two objects are from each other, but if we double their mass, there's no change in force. Something to think about. All right, looking right here, objects with greater mass have a stronger force of gravity between them. So they're directly proportional to each other. So again, if we double the mass, we double the force. We triple the mass, we triple the force. Quadruple the mass, we quadruple the force. Directly proportional to each other. All right, objects that are closer together have a stronger force of gravity between them. And these are inversely, right? So right here, these were directly proportional. These are what we call inversely proportional. Okay. So for example, the moon is closer to Earth than it is to the more massive sun. So the force of gravity is greater between the moon and Earth than between the moon and the sun. Right? So that's why the moon circles around the Earth rather than the sun. Okay. So again, just going back to what I was talking about, when we have a greater distance between two objects, the force is less. When we have a shortened distance, the force is greater. If we double the distance but also double the masses, the force stays the same. All right, so I'm going to actually have Mr. Halpern show you this video right now from his screen, and we'll come back to the notes after that. But you can always go ahead and watch this video, but I'm not going to do that at this time. All right, so we are back after you watched the video. One last little thing right here, and it's for us to kind of think about and to have written down in our notebooks: gravity and weight. So this is kind of a summary. Weight measures the force of gravity pulling downward on an object. The SI unit for weight, like other forces, is the Newton. Right? So when we're doing calculations, the SI unit for weight is a Newton. On Earth, a mass of 1 kilogram has a weight of about 10 newtons, right? Remember we were like 9.81, right? And it kept going on for a while. Well, we're gonna, rounding it to 10, or actually it's right here, sorry. 9.81 newtons is 1 kilogram, right? And so again, make your lives easier, use the 10. All right, hope that helped, and make sure you watch that video if you just skipped by and you weren't in class today. has a lot of important information on it, and so go ahead and get that done. I miss you guys. I hope to see you soon. Bye.